Okay, so I think enough people have joined in. Actually not. Just 9 have joined till now. All right, let's start anyway. So let this plane go with us. So today we will be talking about another application of divide and conquer technique where it is quite useful, and the application is going to be in computing convolutions. Okay, so the topic is going to be convolutions and fast Fourier transforms. So what are convolutions? Okay, so we'll be computing convolutions, and that's where we'll see the application. So suppose we are given two vectors. Let's say A is equal to A0, A1 to AN minus 1, and B is equal to B0, B1 to Bn minus 1. Okay. And now you want to combine or do some operation on these vectors, right? So we have seen, like, in whatever that A plus B, the vector addition, what does it do? It gives a new vector with A0 plus B0, A1 plus B1, AN minus 1 plus B plus 1 as the coordinates, or you can do the inner product, maybe, which is A0 B0 plus A1 B1 plus and B minus 1. Okay, so these are two ways, but there is another way that we will see, and today we'll see why it is important, and hope then we'll see if we have time to get into the algorithm, which is, so this is like summation, this is inner product, but then there is this convolution, A dot B, right? So now this is a vector. Okay, so seems like some construction is going on. So I don't know if that, like, makes my voice not audible, then let me know, and then I'll try to speak louder on top of it, or yeah, maybe I'll use earphones or something, and then that might get more. Anyway, so the convolution of A and B is a vector of okay, so let's not go for dimension, or let's say if A and B both have n things, then is a vector with 2n minus 1 coordinates. Okay, and where the kth coordinate is given by okay, there is a lag, it seems, from what I write in terms of. So summation I plus j is equal to k, 0 less than I less than this one. Am I audible? So maybe this one is working fine. Can you hear
Yes,
me
sir,
properly?
Yes, sir, you are audible.
Let me So the summation is going to be over the indices I and j of a and b, such that the summation of the indices is going to be k. And I have written that, but it's not coming for some reason. So let me see if I. Yeah, okay. Okay. Yeah, now it should be visible, but the drilling has intensified, so maybe I'll speak slightly louder. Okay. So what was I saying? That in the convolution, the kth term is going to be is given by the product of ai and bj's, such that I plus j is equal to k, where I and j are the indices of a and b, right? So basically, this is going to be a vector like so. This convolution vector is going to be whatever a0 b0, because that is the only sum that gives to 0, and a0 b1 plus b1 a0. Sorry, right? Then a0 b2 plus b a1 b1 plus a0 b2 a2 b0, and so on. And finally, you will get whatever a n minus 1 b n minus 1. This is the vector that you get as the result of the convolution. Okay. So, any question about the definition of convolution?
No, sir.
Another way to see it is that, okay, you look. Yeah. Is there a question? Sorry.
No, sir. No, sir.
Okay. So now another way to look at this is, you write these sums like this in a row, whatever a1, b0, or a0, b1, a0, b2, and so on, a0, bn minus 1, and then you have a1, b0, and then a1, bn minus 1, and then you come an minus 1, b0, then you come an minus 1, bn minus 1. So you write it in a like this kind of a square matrix shape. And then what are the convolutions? You take the diagonal, and then you sum along that, right? So first, second, third, so on. And how many diagonals are going to be there? They are going to be 2 and minus 1, right? Okay. So you sum them to get the coordinates of the convoluted vector. Good. So now this can be generalized to vectors of unequal length also, right? So if suppose A is equal to A0 to AM minus 1, B is equal to B0 to Bn minus 1, and then again you do the same thing, that kth coordinate is going to be summation same ai bj, such that I plus j is equal to k. Right? And again, I is less than m, j is less than n. So, okay. So now the question can come that, okay, I mean, we have defined something, but what is the use? Why does this quantity make sense? that you are just summing the coordinates of two vectors, which, like, where the coordinates sum to some number. So, like, there are some applications, actually very important applications, but at first glance it might not seem very intuitive that why we are doing it this way, or what is the purpose of uh, uh, finding a convolution, or summing the products in this way where the coordinates sum to a certain number. So let's look at some applications. So first one is polynomial multiplication. Okay. So suppose we are given, like, a polynomial ax is equal to, let's say, a0 plus a1x plus square plus a minus 1 x to the minus 1, and you are given bx is equal to b0 plus b1x, so on, bn minus 1. So each polynomial can be represented by a vector also. Just like you take the vector a0, a1 to an minus 1, where the ith coordinate is coefficient of x to the I. In the polynomial. So you get this vector a, let's say a is equal to a0, a1 to an minus 1. Then you get this vector b is equal to b0, b1 to bn minus 1. Right? And suppose now we want to compute cx is equal to ax times bx. Right? So now what is going to be the coefficient of, let's say, x to the k in cx? Can someone tell?
So the kth element in the convolution.
Yeah, the k element in convolution. But let's say, so what is the coefficient of x to the k? The coefficient of x to the k is going to be summation of the coefficients, like different ways you can combine the like coefficients of a and b to get x to the k, right? So that will turn out to be ck, let's say, yes, is equal to summation ij such that I plus j is equal to k aibj, right? So exactly, so coefficient vector of cx is convolution of coefficient vectors of a and b, ax and bx. Okay. So if you compute the convolution and you got that vector, that basically gives out the polynomial that you want to compute as a product. Another application which is very widely used is signal processing. So what is signal processing? So, like, suppose we have some real world data that is noisy. Okay. So suppose this data is in the form of a sequence, and let it be a0 to again a vector and an minus 1. And now we want to, since it is noisy, we want to smoothen it out. So we don't want it to be very somewhere a lot of irregularity and so on. So we want to smooth it out. Okay. So how do we smooth it out? So we look at any. So we have this vector. We look at any coordinate ai and take a weighted sum of k on each side. Let's say. And replace it with that. So let ai prime is equal to weighted sum of this and replace ai by ai prime. So we want to take the weighted sum of this much, that okay, we don't look at just the data point, we look at some neighborhood of it, and we say that okay, we are going to find the weighted sum and replace this point with that. We are not going to rely on only this point to get the smoothed out data. Okay. So now, and also this weighted sum, how will this weighted sum look like? This weighted sum should decrease the weights as we go away from AI. Right? Because I mean, we want to be faithful to the original data also. So AI should have the most weight, and as we are going far and far, the distance is increasing. Then we don't want to rely on those values too much to get to AI, right? So one way of at least doing that is called Gaussian smoothing. Let's say. I mean, there can be different ways. And what does Gaussian smoothing do? It puts AI prime is equal to 1 over z summation j is equal to I minus k to I plus k aj times now the weight, and the weight is going to be e to the minus j minus I whole square. Okay. So you see that this e to the this term will decrease very rapidly as you go away from as the difference of j and I increases. Okay, and this z, so here in this k is called width parameter, how much on each side you want to go. Okay, and z is just to normalize so that the weights sum to 1. Okay, good. So now the question can be that okay, we are taking this k on this side, k on this side, and we are looking at this strip. But what about then here, the first k minus 1 elements, let's say, or first k elements? So for them, there is no strip of k on this side, right? So these are going to be the problematic cases, and we are just going to ignore them. So suppose the algorithm, what it does is just removes these guys from the final thing. So this is not there, and this is not there. It only outputs this. Okay? So this is something we will not worry about too much. Okay, good. And then let this W be. So suppose let's take this Gaussian smoothing and let this W be the weights, which is let's say W minus K, W minus of K minus 1, and so on. So this is a vector, W minus 1, W 0, W1, Wk minus 1, Wk. Right? So this is the weight vector that we are going to multiply. So this is basically independent of I. This is the weight vector for every I we will be multiplying with, right? So, for example, in case of this Gaussian smoothing, what is this W going to be? W is equal to 1 over Z, and then you, whatever you get, that this e to the power minus k square, e to the power minus k minus 1 square, so on. Then you get e to the power minus 1, then 0, e to the power 0, which is 1, then e to the power minus 1, and then same thing again, e to the power minus k square. Right? So in case of Gaussian smoothing, it will come out to be this. Good. So now, what do we mean by this weight vector now? That we have this, again, the original vector. And this weight vector has 2k plus 1 size. And what we do, we just like put it here. So this is W. And then we slide it. So we put it here to get this value of AI, then we slide it slightly, then we get this value of AI, and slowly, like, we fill out all the value of AI primes. Right? Any question on this? That how do we do with smoothing? Do this smoothing process? So what we are getting is AI prime is equal to summation. Now WS AI plus S, where S goes from minus K to K. Right? So the first term is going to be W minus K, AI minus K, and the last term is going to be WK AI plus K. Right? And this will see that this is actually a convolution. And to see it as a convolution, we just need to rename things a bit. Okay, so let's define a vector B such that BL is equal to W K minus L. So basically, B is going to be reverse of W, right? So that is B0 is equal to going to be WK, and B2K is going to be W minus K. Right? So you just reverse this W vector. So B is equal to basically B0 to B2K, and this is equal to WK to W minus K. Just to give the correspondence that what this will correspond to. Okay, good. Now let's just rewrite these terms to see how they look like in terms of B. So we have this AI prime is equal to S is equal to minus K to K, WS AI plus S. Right? So now we have this BL is equal to WK minus L. So we also have, since they are reverse of each other, we also have that WL is equal to BK minus L also. Again, you can put the same thing and see how it will work out. And that would mean that this we can write it as S is equal to minus K to K, B K minus S, since WL is equal to BK minus L, A I plus S. Right? And now we want to change the indices. We want to now this K minus S, we want to replace by some L. So K minus S is equal to L, let's say. So now L is equal to K minus S. So if S is minus K, then what is going to be the indices now for the sum? Can someone tell? What are going to be the indices here? What will L go from? What is the range of L?
From 2k to 0.
Yes. So since S goes from minus k to k, when S is minus k, L is going to be k minus minus k, which is 2k. And then when the L is equal to when S is equal to k, then L is going to be 0. So let's say L is equal to 2k to 0, which again, like this does not matter. We can say 0 to 2k also because these are separate terms. So here I'm changing the indices, the order of the indices, but it does not really matter. So L is equal to 0 to 2k. Now you get this BL AI plus k minus L. And now we want to again replace this, suppose I plus k minus L with some j, just to see which index of A gets multiplied, right? So then we get L is equal to 0 to k, BL, AJ, and what is this j? J is such that L and J are such that and so now it is going also from L to 0 to 2k, J is equal to whatever, J is equal to J less than whatever the dimension of N is. So let's remove this and just say that this is L comma J pairs such that I plus K is equal to J plus L, right? Because it should satisfy this. So again, of course, the indices should only go for what they are defined for. You should not go for all L and J. So they should only go for, so L goes from, of course, 0 to 2k, and J goes from whatever the A's indices are. So if A was, let's say, k plus 1, 2, because N minus k plus 1, something like that. Anyway. But the point is that now this is like a convolution, because if you fix I and if you fix I, then what do you get here? Then you get the k is fixed. So for the ith term now, so this is ai prime, right? So the smoothed ith term, so fix I, and then we get that this is ith term in the convolution of A and B, right? Because this is BLAJ, and what we are doing, we are just finding a term in the convolution of A and B such that its coefficients sum to, or the numbers sum to I plus K, right? Where the I is the coordinate of the new smooth term that we are going to find out. Okay, so this is basically just a convolution. So I mean, this was just to show that how do we get the smooth term? We get the smooth term by just looking at this vector A. Then we look at this vector B, not so huge. Vector B is actually very small. And what is vector B? Reverse of the weight vector that we wanted to slide. And then we take, like, AI prime is just ith coordinate convolution of A and B. Okay. Any questions about this? No questions? Okay, so this is so that's what this is another application where the smoothing or the smoothed out vector actually comes out to be the actually just the convolution of the original vector and the weight vector reversed. Okay, good. So now one final application, which is combining histograms. So what is a histogram? Histogram is frequency distribution. So for a number I, you are given like, whatever some frequency of or how many times I occurs in some data. So suppose, for example, that you have AI represents how many men earn I, like value I, or how many, yeah, their earning is I. And similarly, you have a vector. So this is basically a vector that, whatever A0 to something. And then you have BI, which shows how many. So let's say this is A0 to whatever AM minus 1, M length, how many women earn I, and then you have B0 to Bn minus 1. And now suppose you want to find out how many pairs of men, women earn K, right? So you want that, okay, so we have the data for I, we have the data for, we have the data for men, we have the data for women, and now we want the summation that, okay, how many pairs are there such that the total income is K, right? So now how do we find that? So for total income K, look at I and J such that I plus J is equal to K, and then we can choose from AI men and BI women, BJ women to get total income K, right? Total income is I plus J is equal to K. Good. So basically, I mean, so this number is now basically just going to be what? Like this is the convolution. So CK is equal to, so suppose this was the number, how many pairs you want, suppose that was CK. So CK is now simply summation AIBJ I plus J is equal to K. Right? And this, like, this, I mean, might seem like, okay, why do we want to compute, pairs of number of pairs of men and women that on the exactly the same, like, such that the sum comes out to be K. But this, if you look at it in terms of random variables, then it makes a lot of sense that, okay, suppose you have two distributions of random variables. So let's say independent random variables, and want to find the distribution for their sum. Right? Then that is going to be the convolution, because the sum is going to be something, and then you are given the frequency as a histogram or as a function, and that's what you are going to sum them up. Okay. So this is also very important application of these convolutions. So now we have seen like enough applications, and let's start at least computing, or trying to see that how do we compute the convolutions. Any questions about any of the applications? I wanted to spend some time because otherwise it will just feel like that. Okay, what are these things and why are we computing them? Because they are not like the first thing that is taught in a linear algebra course or whatever. So okay, so let's now get into the computation. So we'll consider that vectors of even length, just for our, but it can translate to so uneven also, whatever we'll do, but just for convenience we are going to take vectors of equal length, right? Okay, good. So what is going to be a naive approach?
Calculate all the pairwise products.
Calculate all the pairwise products, right? So for each k we know that this is given. What is the definition? Coordinate, compute the term summation a I b j I plus j is equal to k. So, but so basically, what you're doing is you are computing the whole thing. So find a I b j for every pair, and then find your, and how many pairs are going to be n two, so, or not even order, omega n square operations or theta n square operations, right? And what do you do then? You compute this matrix that we talked about, basically. And then you just sum them up to get these things, right? Okay, good. Now it's not actually choose 2, it's actually ordered pairs, so it is n square. And then you sum them up to get all these values, all the k coordinates, right? So it takes omega n square arithmetic operations. And it seems like, that seems natural because you have these n square partial products, which come in the definition sort of the convolution. But the question is like, how do we show? Can we show that n square are compulsory? And that doesn't seem very obvious. Why? Because input two vectors of length n, so order n size. And what is the output? One vector of 2n size, right? So order n size. So we have to finally compute these order n many coordinates only, right? We don't have to compute n square many coordinates. So how, actually we can say that these n square are necessary, and actually you can do it order n log n arithmetic operations. And this uses the technique of fast Fourier transforms. Okay. So I'll just give an overview of the algorithm, and then tomorrow we'll see that how the algorithm actually works. So how to design the algorithm. So details we'll have a look at tomorrow, but today we'll just have an overview of how the algorithm is working. Okay. Good. So what we are going to exploit is the connection between the first application that we saw. Connection between convolutions and product of polynomials. Okay, good. So what we had said earlier, that convolutions can be used to compute product. But now we want to say the other way around. We want that for product, we use the product, use it to compute convolution. And how? That's very natural, right? That we are given two vectors now, a is equal to a0 to an minus 1. We are given another vector b0 to bn minus 1. So now we associate two polynomials, ax is equal to a1x, sorry, a0 plus a1x plus whatever an minus 1, xn minus 1, and bx is equal to b0 plus b1x plus bn minus 1 x to n minus 1. And now if we can compute the polynomial cx, right? And if we can compute it order and log and time, then we know that the coefficient of cx are exactly the terms in the convolution. Right? So here we will try to now look at the polynomials and see that how using the polynomials now we can compute the convolution, right? So the coefficient of cx will give the convolution vector. So how will we do that? What are going to be the steps? So the first step is going to be choose some 2n points. Let's say x1 to x2n, right? And compute a and b on, let's say, xj for all j in 2. Right? So you compute a and b. So let's say ax and bx, to be more precise, on xj for all j in this 2n, on all these 2n points. Then compute cxj is equal to axj times bxj, again for all j in 2n. So first you compute A on these 2n points, then you compute B, then you compute C on these all these points. And computing C is going to be very easy. You just multiply A and B, right? What you have already calculated. Now you have this C1 in the final step. What you have is C1, C2, sorry, CX1, CX2, and CXN, 2n, right? And what is the degree of C? What is the degree of C? If A and B have degree n minus 1, what is the degree of C?
2n minus 2.
2n minus 2, right? So now, if you are given the value of C on these 2n many points and degree of C is 2n minus 2, you know that a polynomial is is determined uniquely by if we have its evaluation, so polynomial of degree d, let's say. If we have its evaluation on d plus 1 points, this we know, right? So degree of c is 2n minus 2. We have its value on 2n points. So then we use this thing called polynomial interpolation. To get c. Right? So this can be computed. So these are the steps which are going to be needed. So step 2 is easy. Step 2 actually just takes order n time or order n operations. So this is good because we just have these 2n values and we just need to multiply them to get 2n values. But what about step 1 and step 3? Step 1, we want to compute ax only, let's say, for 2n values. How much time does computing ax on one x, like, ax on 1 point, how much time does it take? So if we do it naively, then this itself will take order n time. And then you calculate it on 2n points, then it will take order n squared time. So how do we solve this? What to do here so that it does not take so much time? And then we don't know even about step 3, how to do that. How to get C. Okay. So these are the things that we'll be looking at in the next lecture. And for that, the crucial thing is going to be that choose the points x1 to x2n wisely, so that we don't have to do too much effort to get ax and bx. Okay, so they are wisely means they are interrelated somehow. They are not completely random points. Okay. So this is what we will see in the next lecture, and so we'll see tomorrow, and then we'll finish this topic, and that will also finish our divide and conquer part. And then after the minor, we'll start with the program. Okay. Any questions about this approach, or what we are trying to do?
So why are we calculating for 2n points? Is 2n minus 1 points are not necessary? It is enough for 2n minus 1 points, right?
Yeah. I think also. Because C has degree 2n minus 2. Yeah, it should be fine. I'm not sure. I can clarify this tomorrow much better, but I think it should be, it can be done with 2n minus 1 also. But yeah, that does not make any difference asymptotically, but yes, I'll have a look whether this 2nth point is necessary or not. Maybe not. Any other question? Okay. So see you tomorrow, and thank you for coming today.